connection goes or something like that.
या मैं उसको 1.5 लाख बोल दूं।
हाँ बोल हाँ 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 हाँ
मैं उसको 1.5 लाख बोल देता हूँ और एक्सेसिंग वैल्यू को बोल देता हूँ क्योंकि एक्सटर्नल सर्विसेज की रिक्वायरमेंट है।
राइट
शुड बी एंगेज।
हाँ हाँ
यहाँ पे लिखा ही नहीं है, लिखा ही नहीं है। You can't see the table.
Tandon sir, I think you can start now.
Acha, okay. Just close everything. We are ready. Okay, good afternoon, friends, and welcome to this very special webinar of IAStructE, which is titled "The Story of Morandi Bridge Collapse in Italy." We have our own president, Mr. Alok Bhowmick, giving the making the presentation, and we have two very respected members of our profession and very well-known people, engineer Agostino Marioni and Dr. Harshavardhan Subbarao. I think Harshavardhan Subbarao, you must be seeing him every day in the evening, at least twice a week, when we have our lectures on cable-stayed bridges, which he is moderating. Just to give you a brief of why we are having this webinar, the purpose is, what are the lessons that we can learn from the failure? Because after all, failures are our best teachers. Secondly, we wanted to know a little bit more about engineer Ricardo Morandi, the famous structural engineer from Italy, famous for his bold designs, who inspired a generation of structural engineers, or more than one generation of structural engineers of his time. I think during the mid 20th century, if you really look at it, there were about 4 prominent names that stand out as far as concrete bridge engineering is concerned. I'm not talking about the US at all, because they were way behind as far as concrete is concerned, but they certainly had an equal number of very famous bridge engineers who made it in steel. But as far as concrete bridge engineering is concerned, there were 4 or 5 names which were very famous in the, I would say, in the middle of the 20th century. The first is Freycinet of France, whose name you must have heard. He was the inventor of pre-stressing. Then we had another, later on, another French engineer, Jean Muller, who also made some outstanding concrete bridges. In Germany, we had Fritz Leonhard, who was equally famous. I think he was called the Freycinet of Germany. He was that famous. And of course, there was Ricardo Morandi. So all these people were there more or less in the at the same time in the mid 20th century. About Morandi, I can only quote one of his colleagues, what he has said. He was an engineer with an incredible creativity and was the greatest Italian bridge designer we ever had. And this is, I think, when somebody from your own country and your own profession says that, it has a lot of meaning. And I can only tell you that as a young engineer at that time, in the early, mid 60s and 70s, I too was very inspired by his work. And Alok will show you some of, at least one of the structures which I designed as a very young engineer, which was really inspired by what article I had read about engineer Morandi and his famous bridge in Maracaibo in Venezuela. I would now like to introduce to you our speaker and, of course, today's panelists. Mr. Alok Bhowmick is the Managing Director of B&S Engineering Consultants Private Limited, a bridge expert and a leading consultant. He is the current president of IAStructE, as you know, and an active governing council member of CEAI, that's the Consulting Engineers Association of India. He has accreditation of International Professional Engineer India, and he's an active member of several professional bodies like Institution of Engineers, Consulting Engineers Association of India, Indian Association, International Association of Bridge and Structural Engineers, IAStructE, and some of the code-making bodies like IRC and the Bureau of Indian Standards. The next person I want to introduce, our panelist, Dr. Agostino Marioni. He graduated as a structural engineer at Politecnico di Milano in 1966. So he's also from Italy, as you can guess from his name. He founded Alga Italy in 1969 and was chairman until 2012. Alga has been a pioneer in the field of bridge bearings and anti-seismic devices and repaired the Pier 11 of the Morandi Bridge in 1993. He is currently chairman of HIRUN International of Taiwan. So Dr. Marioni was actually intimately connected with this bridge. So the insights that we will get from him will be priceless. And we shall do that after Mr. Alok Bhowmick's presentation. The next panelist that I want to discuss or talk about is Dr. Harshavardhan Subbarao, who is the chairman and managing director of the leading firm of Construma Consultancy and holds a PhD from Imperial College London. He is the governing council member of IAStructE and is vice president of International Association of Bridge and Structural Engineering, IABSC as it is called, located in Zurich. He is a member of the Highway Research Board of India and serves on several committees of IRC, Bureau of Indian Standards, and various international and national bodies, But what I particularly want to mention, his association and his relevance in as being today's panelist, is that he's a member of the IABSC task group of forensic engineering. As you know what forensic means, it means to investigate any collapse that happens in structural engineering. That is what it is all about. He is also a member of the IABSC task group, which looks after the database of failures. And finally, of course, he is also on the editorial board of forensic engineering of the internet of the ICE in UK, which is again on forensic engineering. So you have actually two specialists panelists, Dr. Marioni, who was connected with the bridge itself, which we are going to talk about, and Dr. Harshavardhan Subbarao, who's connected with so many international bodies as far as forensic engineering is concerned. So with these opening remarks, may I now hand over the mic to Mr. Alok Bhowmick, who can start his presentation. Thank you.
Good afternoon, all the panelists and the participants. Am I audible?
Yes.
Thank you. Thank you. So once again, very good afternoon to all of you. Today's presentation is, as Professor Tandon mentioned, the story of Morandi Bridge collapse, Italy, which happened about little more than 2 years ago. And this is, as Professor Tandon in his opening remarks mentioned, that this is made with the intent to disseminate knowledge about the structural failures. Some of you might have attended, a panel discussion which took place last month on 25th of September, which was on structural engineering practice in India. And we, I think, Professor Sudhir Jain, Professor Tandon, Ms. Alpa Sheth, and Mr. Manoj Mittal, they were discussing about introspection and the way forward. And in that discussion, one of the panelists, Ms. Alpa Sheth, mentioned that we in India do not discuss about failures at all. We try to bury it under the carpet. And to a large extent, I agree with her. And but I can just tell you that in Indian Association of Structural Engineers, we have been quite bold, and we have been discussing to the extent possible, the failures. And we have published in last two newsletters, we have been publishing about failures, recent failures in India. Many of these articles, unfortunately, have caused discomfort also to some of us, because the authorities, after reading the articles, have expressed their displeasures, because that is the way of life here. And I still would request, in fact, through this medium, all the participants, if you have any story of failures to share with us, please contact us in our association. And if you have a story to tell, we can provide the platform. We can have similar discussions in future. So with this, let me start my presentation. Morandi Bridge collapsed on 14th of August 2018 in the morning session, forenoon, around 11:40, 11:30, around that time. And 43 people were killed during this collapse. And the bridge, as Professor Tandon mentioned, was designed by none other than Professor Ricardo Morandi, a very famous, very renowned bridge engineer, a structural engineer of international fame at that time, even subsequently also. This is the broad outline of my presentation. I will talk about the bridge. I will explain about the structural arrangement of the bridge. Then I will spend a little time about discussing about the designer, Ricardo Morandi and his works. We have to see this bridge design and the failure in the context of the works done by Ricardo Morandi. We will discuss about the history and maintenance of the bridge, what has happened since its construction in 1967 till its failure in 2018. The at present, the inquiry and the investigation, forensic investigation is still on. The report is not yet out. So therefore, whatever possible causes of collapse we will be talking about will be based on the information which is available in public domain. There are, works done by individuals, academicians, but not the final version. The final version is yet to come. It is hoped that by December, the report will be in public domain. Then I will spend some time on also discussing about the demolition of this partly collapsed bridge, how it is done. It is a very lot of learnings, even from the demolition of the bridge, which took place subsequent to a part collapse of a particular span of this bridge. And also some time I will spend on the new bridge, which is already in fact executed. It is already in service. In a record time of 2 years post collapse, a new bridge has come up there. And in fact, this whole journey from the collapse of the bridge to the inauguration of the new bridge is something which is amazing story, which, for every civil engineer and structural engineer, I think it is worth emulating. So let us start with the first part, which is the collapsed Polcevera Viaduct, as we call it also as a Morandi Bridge. This was an example of advanced engineering for a bridge at the time of its opening. This is the structural arrangement of this bridge. This is about 1 kilometer long. It has got 11 spans, out of which the 3 spans are with cable stayed structure, and the maximum span is 207.88 meter, almost 208 meter. But there are 3 spans which are considered, long spans, which are having spans 142.66, 207.88, and 202.5 meter. Rest of the spans are in the range of 73 meter, 43 meter. You can see that the spans are varying. There is a lot of variation within the structural arrangement. But there are some standardization done, which I will explain to you later. Before that, let me just tell you the importance of the city Genoa, where this bridge is there. I mean, Genoa is it's a port city. It's a very happening city in Italy, because it is one of the busiest port in the Mediterranean. And the particular bridge is a part of a motorway which is called A10 motorway. This is that A10 motorway, and this motorway, connects France with Italy. And in fact, the traffic here has gone up from, since construction, almost like many fold, about 10 to 15 fold. The traffic has increased over this particular corridor because of its importance. And it is a huge infrastructure. If you really see, a bridge in an urban habitat, having a cable stayed concept with the height of this tower is nearly 45 meter from the top of deck, and the deck itself is about 45 meter from the rail level or the ground level. So it's a very gigantic bridge, and the bridge located in the heart of the city of Genoa. This picture shows the bridge as it existed. The one on the left hand side gives you a picture of the bridge as it existed just before the collapse. That means in the month of August, early August 2018. And the same bridge way back in 1967, just after construction, is shown on the right hand side. Below, you can see at the time of inauguration, Professor Morandi, this is Professor Morandi, and he is explaining to the president of Italy, Giuseppe Saragat, during the inauguration of the bridge, about the bridge. The model of the bridge can be seen here. And what you see on the extreme right bottom is the inauguration which is actually taking place. That inauguration is on 4th of September 1967. These are few pictures taken just after the collapse of the bridge. I mean, the amount of devastation is visible here. You can see there are 3 towers, out of which 1 tower is missing. That is what has collapsed. And this tower, if you see the previous general arrangement drawing, this is the tower which is called P9, which collapsed. There are 2 towers which are P10 and P11, which did not collapse, which was subsequently demolished. So this is P11, this is P10, and the P9 has gone. And what I will try to show you is a small clip of about a minute of the actual collapse, which was captured in one of the camera. This is just a small clip, just to show you how the bridge collapsed. Now, subsequent report shows that the bridge collapsed due to failure of one of the tie of P9, which led 1 out of the 4 first collapsed at the top, and subsequently, because of the torsion, the bridge collapsed. I mean, it is sequentially, progressively, it collapsed. Though from the video, it is not very clear, but it is based on the reports. The most authentic part will come only when we get the final report from the investigation agency. Now, let me discuss a little bit into go into the structural scheme of the bridge, so that we understand, in little greater detail structurally. You see, this is a typical Morandi bridge. I mean, this is a signature of Morandi. The signature of Morandi, how is it different from the other cable stayed bridges? Is that a Morandi bridge is basically a purely concrete bridge. Even the stay cable is made of concrete. The steel is encased by concrete, and therefore it is a pre-stressed concrete tie, which is unique of Morandi design. And the typical, this particular bridge, Genoa Bridge, was constructed in 1967. And prior to that, about 5 years ago, he became very famous internationally because of another bridge, which is Maracaibo Bridge in Venezuela, which was completed in 1962. And that was also of similar type. I will discuss about that later. And this is almost similar to that. But the uniqueness of the Maracaibo Bridge, or this particular bridge, is that it has got a A-shaped frame. You can see this A-shaped frame which connects the top of the stay cable, and the deck is connected by a V-shaped pier. You see, this A-shaped frame, if you can see here, is not connecting the deck at all. The A-shaped frame is only supporting the stay cable, and the stay cable connects the deck. And the deck is supported at the bottom, from the bottom, by trestle or frame. And this V frame and the tie holds the deck. And this deck, out of this 210 meter, there is a suspended span, which in Europe they call Gerber beam. And this Gerber beam is nothing but a suspended span. And the uniqueness of this particular bridge or standardization, though you may find that all the spans are different. You have 43 meter, 73 meter, 142 meter, all spans are, a lot of variations. But there is one commonality in all span, that they have suspended span or Gerber beam of 36 meter everywhere. So this is a pre-stressed concrete girders of 36 meter, which is embedded in all the spans. So every every span, which is 73.2, has got a V frame with a in situ deck, but at the center you have a 36-meter precast PSC girder with in situ deck slab suspended span. They call it a Gerber beam, which later on, after a little bit of research in Google, I found out that Gerber is the name of the German engineer who invented this concept of suspended span, because by using suspended span you can reproduce the behavior of a continuous bridge. At the point of contraflexure you provide a articulation, and that concept we use in India, we used to use in the past, and of course nowadays it is being discouraged, but this concept has been used extensively in this particular bridge. It's called Gerber beam. And you can see here this Gerber beam between the suspended span, and you can see this arrangement. I think this particular view, gives you in little more detail. Broadly speaking, if you take one particular span, which is 200 meters, it has got, you can see the 36-meter is the suspended span, and from the center about 86-meter is the arm of this deck, which is having in the concrete tie. Beyond the concrete tie, only about 10-11 meter of cantilever of the deck, and on which this suspended span is supported. At the middle, you have about a V frame. This V frame is supported about 40 meters. This span is about 40 meters, about 20.6 meters from the center on either side, where you have this leg of the V joining. And after collapse, this is the picture on the right bottom, and you can see how this V frame on the approaches are there. In between you have this suspended span or Gerber beam, etc. So I think from this drawing or the sketch, you can get a fairly good picture of the structural scheme that is there in Morandi Bridge. As far as the main deck is concerned, it's a PSC box girder, 5-cell PSC box girder, which was constructed by cantilever method of construction. The portion within the V was constructed cast in situ, but thereafter the cantilever construction, about 5 meter, cast in situ cantilever construction was adopted. And this is a very interesting part, which I will discuss as we move forward. This is the kind of terminology they use for the deck P9, which collapsed. These are stay cables. These are concrete stay cable. The A frame which supports the stay is called antenna. And as I mentioned, the suspended span is the Gerber beam. This is the deck. And this deck also is very interesting. If you see in between, this is the soffit of the beam. There are three. It's a 3-cell box girder, but in between the soffit is missing. The soffit, if you cut a cross section at the middle of this PSC multi-cell box girder, the soffit is there only in 3 continuously, but near the supports where this V frame is joining, you can see that the soffit slab is full. So wherever you need the compression at the bottom, the soffit slab is increased as per the structural engineering requirement. So one of the uniqueness of Morandi design is he believed in flow of forces and giving optimization of design. I think recent lectures that we are hearing from Professor Holger Svensson about cable stayed bridges, we hear the same thing. There is a lot of emphasis on economy of design and optimization, and I think the particular detailing reflects this very clearly. These are the broad dimensions of the structure. Let me start from the foundation. The foundation, as I gather from one of the literature, is that there are 40-meter deep pile foundation, 1.2-meter dia we used for the support. The pier has got inclined 8 inclined struts. You can see these 4 this side and 4 that side, and they are of dimension. They are variable dimensions, varying from 4.5 meter to 2 meter at the top. The transversely dimension is fixed 1.2 meter in the transverse direction. In the longitudinal direction, it is varying. The A-shaped frame, as you can see, which supports the stay cable, is a hollow box. It is not a solid, it is a hollow box. And it has got a dimension, outer dimension of 4.5 meter. Thickness of the concrete is 0.9 meter. And at the top, it goes down to 2 meter. The main deck I mentioned is 5-cell PSC box section. The transverse link girders connecting the stay and the pier are these concrete ties. I will discuss in greater detail about these ties. And you have the two simply supported Gerber beam spans connecting this system. Now let me discuss a little bit about the difference between Morandi Bridge and other cable stayed bridge. Uh, what you see on the top is the typical Morandi Bridge I mentioned, which has been reproduced only at three places. Morandi Bridge, first in Maracaibo Bridge, Venezuela, followed by this one, Polcevera Viaduct, and at other places. But one unique thing about Ricardo Morandi is nowhere he has completely copied the design. Every design may look outwardly similar, but there are distinct differences. The new bridge, whichever he has done, he has always improved on the first one. For example, in Maracaibo Bridge, Venezuela, he did not use the encased concrete tie. He used the normal steel tie. But he realized probably after the construction and while doing this Genoa bridge, he changed the nature of tie. He encased it in concrete and then did pre-stressing in the second stage as well. Now the distinction between normal conventional cable stayed bridge at that time or even today for that matter, and Maracaibo or Morandi Bridge is that there is only a single tie which Morandi used, whereas the conventional practice is to use multiple ties. Today, when we look back, we certainly find this multiple, cable stayed bridge of the type being used are obviously has got many distinct advantages as compared to the Morandi's single tie. First of all, there is redundancy, and even if one particular tie goes, the structure will not collapse. Today, in cable stayed bridges, that is one of the criteria based on which we do the design. Whereas in one of the reason for failure of this Morandi Bridge is the lack of redundancy and robustness, which is a requirement today. But you have to look at it in context. In 1962, when he conceived these bridges, the concept of durability, the concept of redundancy, and the concept of robustness was not discussed, was not an issue which came to the minds of people at that time. It was only much later, in 70s, when bridges started deteriorating, that the concept of durability, robustness, and all came as a sort of an important criteria. Another disadvantage of this Morandi concept is, unlike a normal routine conventional cable stayed bridge, is that you see if you have cables at very close interval, then your design forces for service condition in the deck and design forces during construction are not much different. You don't have to use auxiliary support or auxiliary methods during construction. In case of a single tie, the one of the disadvantage is, for example, when this cantilever construction of the deck is being done, such a large cantilever, the construction stage starts governing unless you find some other way of temporarily sort of safeguarding the deck. And this is precisely what Morandi did in this particular bridge during construction. He used auxiliary strands to reduce the permanent structure, the PT cable in the permanent structure. And after introducing this tie, those auxiliary strands were removed. So this is not required in case of a conventional routine multi-stake cable stayed bridge. Another interesting point which needs to be, put in our mind when we discuss about the Morandi Bridge is that at the time of its conception and at construction, there were not many cable stayed bridge in the world. This is a chart which shows what is the maximum span length with the year of completion, and you will see that at in the year 1960, 61, 62, there were not many bridges having span length more than 200 meter. I mean, it is you can only count. You had the Stromsund Bridge, and you had one, two, three, or four bridges. So it is not that the experience of cable stayed bridges were many. So in light of this, Morandi was one of the pioneer or a creator of the concepts in terms of cable stayed bridge. So at that time in 1960s, 60 early 60s, it was there are two theories or the two type of cable stayed bridges going on. One was with stay cable, and the one was with concrete tie, and both were equally popular. Only with time you will see more and more number of repetition of the stay cable system, and less and less use of this Morandi concept in stay cables. Now, let me get into the little bit of construction details of this particular bridge. Construction photos of those days, 60s, reveal that the traditional methods have been used for the design of substructure. You can see the piers, these tall piers, 45-meter high piers, and the this part of the deck is done cast in situ with staging, very conventional and traditional method. And you can see here various stages of construction, which is, I think, self-explanatory. This shot shows each of the three towers. This is P11, P10, and P9 in various stages of construction. Very interesting photograph, because in one photograph you can see all the three stages of, P11, for example, the tie is already in place, and the only the Gerber beam or the suspended span is to be placed now. Whereas if you see the second P10, P10, the A-frame is completed, and the cantilever part is almost completed. It is time now to put this tie. And in P9, this is the one which collapsed eventually. You can see that it is just the central portion of the PSC box cutter which was completed, and the cantilever construction is yet to start. This is another picture which shows, there are two pictures which shows the cantilever construction in progress, a conventional cantilever method. But what is very interesting here to see is the auxiliary strands. If you see on top of the deck, you have these auxiliary strands, and these auxiliary strands are required because we have a very large cantilever, and this cantilever eventually, once the tie comes in place, will not be cantilever, and therefore in the permanent stage you don't require that many cables, and in the temporary stage auxiliary strands are used to reduce the use of permanent cables. You can see this is another picture subsequent to this, where you can see that the cables are now being installed, and this is the bottom. This one shows these auxiliary strands on top of the deck, how it is being placed. This is uh, uh, the blown up view of the concrete tie, which I want to spend some time on this. If you can see carefully, this stay cable consists of two distinct stays. If you can see here, there is a gap. So there are, if you see, the concrete stay is bifurcated from somewhere here into two separate concrete ties. So if you cut a section here, there are two independent concrete stays, but as you go up, it joins and it becomes one. Uh, uh, this is the cross section at, if you see one cross section here, so there are set of cables here, and if you see cross section here, there are, so the cables are of two types. You can see the A cable and the B cable. The A cable is the one which is first stressed. The A cables are stressed raw. That means at that there is no concrete. So first you stress these set A cables, which are 24 numbers, and once these cables are stressed, the deck is actually supported. Thereafter, these set A cables are encased in concrete. While encasing the concrete, you leave the set B cables, which are 26 or 28 in numbers, but they are smaller in size. You see, these A cables are the predominant main cables, which are, those days strands were used, and 28 numbers. I mean, each cable comprises of either 16 or 12 numbers of strands. This is the set A cable, and in set B cables, they are smaller. They are only 4 strands each cable. So though numbers is 28, but they are comprising only 4 strands of cable. So they are smaller in numbers, and they are done post concreting, and they are not stressed to the full. They are stressed only partially. This is only to ensure that the main tension is taken by the original cables which are stressed raw, which are subsequently encased by concrete. And second stage cable is used to only take the live load stresses, just to ensure that this pre-stressed tie is always in compression even during service. And you can see that this, if y- I you can see, I don't know whether it is visible, this red line, a straight line. If you join between the two, you can see a sag, a distinct sag, and that sag is obvious because the raw cable, first you stress the raw cable, it has got a sag, then you put concrete casing of concrete in top, so there is a sag. So the second stage cable cannot be stressed too much, because then the p delta effect will start dominating. So very carefully the second stage cables have been stressed. This is another drawing of the cable. These cables are having a saddle on top, or through which it is passed. And this is a blown up view on the right hand side to show your cable set A and set B. The bigger diameter ones are set A cables, which are stressed first, and the red ones are the set B cables, which are stressed after the concreting. These are some photographs which shows during at the time, how these cables were sort of laid. And then you can see on the left hand side these cables are being laid. That is the set A cable, the blue cables, and you can see that that is stressed. First stage cable is stressed here. And then this is another picture which shows, you see, this is P10 and this is P9. And in P10, you can see the cables are already stressed, so it is stretched. And in P9, the cables are being laid, it is not yet stressed, so it is yet to take load. So you can see in P9, these auxiliary cables are there, but you can see here the auxiliary cable is gone, because this, once you stress this cable, you can remove the auxiliary cables. This is another picture which shows, encasing after stressing, it is being encased for concreting. So all these are invaluable pictures which I could get from one of the journal, which is of course there in Google. You can search and get it. This is a picture which shows how the Gerber beam or suspended span is being erected by using truss on top, supported from both side cantilever, which is a very conventional method for suspended span. Only thing is, in this case, the suspended span is pretty large. Uh, 36 meter is pretty large. Uh, this one shows a little bit pictorially the various phases of construction. The first phase, you do everything cast in situ by traditional method. Then you do cantilever construction, use temporary cable, auxiliary cables to support it. Then you put cable A, which is blue cables, and after that you encase the cable in concrete, and then use cable B. And once that is done, you put the Gerber beam. So this is the sequence in which construction is completed. Uh, the timeline followed for the new bridge post collapse is amazing. I mean, this is something which is, you know, worth emulating, as I mentioned earlier. 14th of August 2018, the bridge collapsed. 9th February, demolition of the Morandi Bridge begins. In between, there are so many activities. On 15th of April 2019, the reconstruction officially begins with the placing of the first pile. And on 3rd August 2020, the new bridge, which is 1 kilometer long, with a completely new design, and you know, it's a state of the art, is open for traffic. So I think a lot of lessons to learn, even the post-collapse scenario, how you know, the bridge, the project has been handled. Now let us talk a little bit about Ricardo Morandi, the uh, designer. Professor Morandi is, of course, as I think we have talked about him a little bit enough. He is a visionary, a rare example of an original artist who devoted himself to civil engineering. He was always innovative in his design, and anything that he did is something which is worth discussing. He graduated in 1927, and initially, first phase, he worked on some earthquake damage areas, you know, and there he spent some time. In 1948, his research allowed him to obtain the patent of his pre-stressing system. Just imagine, 1927 graduated, 1948, that means in 21 years, he has a patent on pre-stressing M5 system. Uh, he was appointed professor of bridge design both at the University of Florence and the University of Rome, became a fellow of the Royal Society of Encouragement of Arts, Manufactures and Commerce in 1963, and got an honorary doctorate in architecture by Technical University of Munich in 1970. Two protagonists, undisputed protagonists from are Narvi and Morandi, and they almost at the same time they used to practice both. uh, you know, they were competing with each other. At the same time, they had a lot of respect for each other. In many of the talks which Professor Morandi gave, he mentioned about Narvi, and many of the talks which Narvi gave talked about Morandi. They had such an excellent you know, communication. But yeah, interestingly, both had completely different style of, you know, design. Their design, while Narvi's design had a trend, which is, you know, slender structure, which is symmetrical, static balance, whereas the Morandi's structure seems to be completely different, which is you know, respecting the flow of forces. It will be a conventional structure, a little bulky, but always sort of you know, both the designers had their own unique style. Some of the works of Ricardo Morandi, initial stage, you know, uh, after his initial 5 6 years in damage assessment of earthquake, you know, buildings in earthquake damaged buildings, he went into his consultancy and started working on large span structures. Yes, he started designing cinema halls, and he became very popular in Italy. Many of the cinema halls with large roof structures were designed by Ricardo Morandi. And those days, the cinema hall, the producers, Gemini, very well known. Practically all the cinema halls of Gemini was done by Morandi, Ricardo Morandi. And every cinema hall had some uniqueness in terms of structure. Time will not permit me to go through that, but it's very interesting. If somebody wants to go into the details, can, you know, go through the Google search and do it. Bridges was his, of course, passion, and you can see each and every. It's not only just the cable stayed bridges, but even arch bridges had some uniqueness. You can see it is very unconventional to have the piers which are inclined, and every pier has got a different inclination. And if you go through some literature, you will note why this inclination is there. This inclination, is done purposely so that because the deck imparts a frictional force due to shrinkage, temperature, etc., and the inward force is more. So the piers are purposefully inclined so that the net bending moments are reduced in the pier, because the resultant force direction is always towards the crown of the arch, and that is what he has taken into account in his arch designs. And this is also this Ponte Morandi in 1953 in Italy. This bridge is also unique in the sense that it has got a simply supported span on an arch on both sides. These are the two different bridges with inclined piers, which is supporting the deck. And this is, of course, the famous Maracaibo Bridge. Uh, since 1945 till 1987, Professor Morandi passed away in 1989, but he has been designing a number of bridges from 1945. This is the list of Ricardo Morandi bridges in chronological orders from 1945 till 1986-88. The last bridge which he designed, Rotaro Viaduct near Lauria Potenza. Each and every structure is unique. I think there may be another webinar on Morandi bridges alone. Let me talk a little bit about this famous Maracaibo Bridge, because that is the bridge in which Ricardo Morandi achieved the international fame and acclaim as a master builder. And he was called after this bridge Le Corbusier on four wheels. Le Corbusier, of course, the name we are quite familiar with, because he is the master planner of Chandigarh, our city of Chandigarh. Le Corbusier was one of the famous architects who is about 10-15 years senior to Professor Morandi. And at that time, when he was in business, Le Corbusier was very, very popular. So naturally, when Ricardo Morandi came out with such excellent bridge design, so he was called the Le Corbusier on four wheels. This was an extraordinary mega structure, 9 kilometers in length. Professor Morandi also designed several airport hangars with his unique style of pre-stressed concrete ties, and this is one such example. This is Leonardo da Vinci International Airport in Rome, designed by Ricardo Morandi and completed in 1961. You can see the soffit of the roof, which is inclined with the tip, which is raised up, essentially to accommodate the tail of the aircraft. There is also another similar airport maintenance hangar at Fiumicino Airport, Rome, for Boeing 747. All these, examples of some masterpieces by Professor Morandi. Professor Tandon was mentioning in the opening remarks about a hangar, which is also on the similar concept designed by Professor Tandon, inspired by the work of Professor Morandi, and this is the one, which is a airport hangar in Mumbai for Indian Airlines or Air India, whatever you call it. And I would request Professor Tandon, maybe after my presentation, to speak a little bit about this particular structure, which is exactly on the similar lines as, with pre-stressed concrete type. This is another view of the same with molded plate. I mean, I think there are a lot of uniqueness on this. This must have been done in the late 60s or early 70s. Professor Tandon can throw some light on this later. I just wanted to share one more thing about Professor Morandi to end with this particular section. There was a lecture delivered by him in November 1961 at the Institution of Engineers, UK. And give me some 2 minutes to just read through some part of his speech, which is very, very interesting. And I read, this talk he is giving, on his paper, which is titled Engineering and Architecture. And he says, I mean, I've just picked up a part of his speech. He says, I, who speak to you, am an engineer, a structural designer, that is, a man who has been trained by the schools of his day to act as an intermediary between the ideas of the architect and the requirements of the constructor. The man who in Italy is still called the calculator of a work of engineering. I began, therefore, to be a calculator of structures in reinforced concrete. And at first, my clients required nothing more of me than a structure which adhered exactly to the dictats of the designer, that is, the architect. Economical, easily built, and statically correct. Collaboration with the architect has often been pleasant and uh, and fruitful, but I remember many bitter moments when I remember many bitter moments when the architect and the client could not understand that the calculator might have his own sensitivity and above all an understanding of possibilities of the stylistic expression of the materials which he had learned to deal with. That was a time when there was still an absolute separation of engineering and architecture, a reminder of the positivist outlook, a technical literature, especially found calculated casuistry, almost as if a good set of formulas could take the place of an engineer with his sensibilities. A young engineer with its cold reasoning. Such was the preparation of a calculator in those days. All those cases in which masterpieces of engineering were also and essentially masterpieces of architecture. The Fourth Bridge, Eiffel's Viaduct over the Garabit, Maillard's bridges, Fresine's hangars at Orly, Henry Bick's Risorgimento Bridge, Nervi's first works were not yet being considered by the critics. In 35 years ago, men of culture in Italy were still discussing the style of Vignola. Vignola is an architect in Italy, and its use, even though under the tympanums and classical arches, a solid reinforced concrete beam, carefully hidden, happily performed their statical function. At a certain point in my life, I refused to be relegated to the formulas, and little by little, helped by the evaluation of the times, and especially by the ever increasing liberty provided by the new techniques, I learned to express my own personal style. I think I very much liked this part of his speech, and I think it speaks volumes of what we are facing today, and I think a lot of lessons to learn from this. So I come to the third part, which is history of maintenance of the bridge. I will be quick now. I've already, I think it is 1 hour past, so I think I should be able to finish it off in next half an hour. History of maintenance of the bridge. The bridge, had shown the sign of distress and excessive deflection very early since its birth. I mean, this problem were visible right from, the construction. Professor Ricardo Morandi himself was surprised to see the structure age faster than he had anticipated. Very interestingly, in 1979, he was a part of the working commission of IAStructE, and in one of the report in 1979, detailing a number of interventions to protect the structure against pollution from nearby factories and salty sea area. So this is a document available in IIBAC, in which in 1979 he published a paper in which he talked about this Polcevera Viaduct at that time, and he mentioned that this bridge is certainly requiring protection. And I will just read from that particular report one page. It appears that the structure is struck directly by the marine waves. The sea is about 1 kilometer away, which are canalized in the valley crossed by the viaduct. Therefore, it is a highly saline atmosphere, which also finds on his ways before reaching the viaduct a curtain of fumes from the chimneys of steel mills and therefore becomes saturated with highly noxious vapors. In the besides some small imperfections of execution, which caused some small rust spots to appear on isolated areas due to insufficient end cover of reinforcement, the project has carefully placed within the concrete all steel elements, except, of course, the cadmium lined plates of the bearings for the simply supported girders. All these plates have been literally corroded in little more than 5 years by the extreme and aggressiveness of the atmosphere and had to be substituted with rather complicated process with stainless steel elements. So he confides in 1979 that that within 5 years of the execution, a lot of corrosion he witnessed in the bearings, and he also suggested a lot of protection to the concrete. But he defended the design of the concrete tie by saying that it is only because of the concrete encasing of the cable that the structure is sort of protected against the vagaries of weather. At that time also he mentioned that the design because of this encasing by concrete, but it was later proved that actually the encasing has prevented proper inspection of those cables and even replacement of those cables. This was afterwards, but at that time in 1979 he mentioned this. In the early 1990s, during maintenance and repair activities, it was discovered that the structure had widespread deterioration, and many interventions were done in between. Major strengthening intervention in Pier P11. I think Professor Tandon mentioned in the opening remarks that one of the panelists, Dr. Agostino Marioni, has worked in this. I would like to hear from him after this presentation about the strengthening intervention on Pier 11 for stay cables.
Okay.
Extra new cables added around the corroded ones. Then for Pier P10, the interventions were limited and was mainly concentrated in the section stretching to the crossbeam at top. I will show you that diagram. For Pier P9, which actually collapsed, no intervention of any type was contemplated at that time in 1990s. The attention was focused on the stays and not on the deck or transverse link supported span or pier elements. All these interventions or the diagnostic report seems to suggest problems only with the stay cable, and all the works done primarily focused on the cable, but not much on the deck. So what you see here are the three. At P9, you can see that no intervention took place. This is post 1992. At Pier P10, you can see at the top of the section between the A-frame and the tie, the steel, strengthening was done through using steel plate. Whereas for P11, the entire, new set of cables were inserted, which is external. It is no longer within concrete, but keeping intact the existing cables, additional cables were placed, surrounding the concrete encased tie, or yeah. So this is just a blown up view of P11, where you can see the repairs which were carried out in Tower 11, and these are the cables which you can see on concrete tie. And this is what is in P10. You can see a blown up view where you can see that this particular junction has been strengthened. But subsequent to 1992 also, there has been further distress and deterioration during the period 2011 to 2016. Many experts thought that these are basically due to 2010 floods, which devastated the area, and this was brought to the notice of the authorities. But unfortunately, post 2010 floods, this Morandi Viaduct was not in the list of urgent intervention by the authorities. consequences, the detachment of the concrete cover, this concrete cover started deteriorating and falling, carbonation and oxidation of the reinforcement. So this, you can see the sacks where networks are placed to avoid the material losses. So basically, bridge started deteriorating and the deterioration was progressing. But I think not much of attention was given to the degree of deterioration. Probably the authorities did not realize that this will lead to a collapse one day. So if you see the history, of the maintenance, absence of injection motor is seen both in the stays and the deck cables. In two cables in a precast beam, 4 wires were found fractured. This is in 2011, and all wires were found movable by hand, having thus lost any tensioning. In some cases, an apparent loss of post tensioning is reported in 2011 to 2015, and presence of oxidation and corrosion was also reported of the examined reinforcement, with estimated extension between 10 and 13%, 30%. This is in 2015. This is a diagram, of course, this photograph which shows post collapse, of course, and you can see the extent of damage which they could see after collapse on various cables. Out and somewhere you can see that this is the sheathing. This is the sheathing uh, which is there. So let's come to the possible cause of collapse. There are various possibilities. There, incidentally, there is a IABAC, paper by Professor Calvi, post collapse, in which at that time he was not a part of the investigation agency. Subsequently, he became a part of the investigation, team. But at that time, he published a very highly technical paper on the this particular Morandi Bridge, and these are the possible causes of collapse he identified. One is the construction activities at the time of collapse. It appears that some work was reportedly going on at the foundation of the collapse span at the time of collapse, though subsequently he ruled out that as a possibility of collapse. Design and construction errors. Many raised question about the flawed design of Morandi Bridge concept with single tie, lack of redundancy, robustness and durability, and flawed assessment of creep. Well, this again is something which today, in hindsight, we can always talk about this. But at the time when he designed the bridge, I mentioned that this was unique, and this was one of the sort of most celebrated bridge type. Whether the event took place during an extreme summer storm, and many people give the theory, many experts gave the theory that there was a lightning, and that lightning caused explosion of one of the oil tanker which was moving at that time. Increased traffic. The traffic increased many-fold in terms of volume as well as in terms of axle weight. 25 million vehicles passes per year over this bridge. Weight. Over the last 50 years, the bridge was subjected to overlays several times. Poor maintenance. The bridge needed more attention than it got. Privatization. The bridge was owned and managed by a private entity, not a municipal government agency. They may have not had adequate funds to upgrade the bridge to withstand current demand and meet today's design standards. Infrastructure issues. The infrastructure spending in Italy has been inadequate for decades. This likely contributed to the structural decline of the Morandi Bridge over time. An accident by explosion due to lightning strike, I mentioned about it. So these are the possible causes, and honestly, the failure could have taken place not due to any one single out reason, but a number of them put together. This is the journal or the literature which I was talking about, the paper by Professor Michel Calvi, Gyan Michel Calvi, and his team. This was published online on 20th of December 2018, and it is a published document of YABSE, Structural Engineering International. And one who would like to go into details can read through this particular paper. So what it does a extensive study of four possibilities of failure. One, only the stay cable failure, the stay cable plus the deck failure, only the deck failure, and the suspended span as the trigger for collapse. And all these four possibilities, he has gone into great detail, and he has sort of all the possibilities. Very interestingly, he used a advanced element modeling technique to see the possibility which triggered the failure, and thereafter studied the failure pattern and the debris which was found lying, and the one which where the debris, the way it failed, matched with the collapse mechanism, seems to be the most likely reason for collapse. That is how they did the study. Very interesting. So this assessment and explicit modeling was done in a software which is called AEM. And these are some of the views of that software. You can see the entire structure is modeled. And if we let me see if I can show you a small animation of that, if it is possible. I don't know. Yeah. So I will just show you a small animation of that. Uh, it's a 3-minute animation. Oh, it is taking time. You see, the difference between this finite element method and this advanced element modeling is the fact that in finite element method, which we use for our conventional structures, there is a continuum. Whereas in a failure, there has to be a discretization, because once it fails, then the progressive failure, that model is inapplicable. So this advanced element modeling takes into account the progressive collapse. There is a combination of finite element continuum as well as the discretization. That is the beauty of this particular method. So what it is showing is the various modeling of the various component. These are those Gerber beams or suspended spans. You can see that. So the whole structure is basically modeled, including the pre-stressing and the reinforcement, and it is subjected to various loads. And now you can see the failure. You see, this kind of modeling is not possible in finite element modeling, because once the continuum breaks, thereafter it is not possible to handle in FEM modeling. And now it is, you can see the actual photograph, actual video is being matched. So, so this is the final outcome which Professor Kalvi mentioned in his paper as the possible cause. After doing all these studies, he mentioned that all elements with no exception had ample margin. So therefore, he started, one by one ruling out all other possibilities of failure. For example, he mentions all elements with no exception had ample margin of safety towards failure, considering the structure as described at the time of construction. The addition of variable live load seems to have little influence on the assessed demands, thus being unlikely trigger for failure. An exceptional point load acting on the critical section, that is, may induce local element collapse, particularly in presence of relevant progress of corrosion. This he is talking about that possible likely explosion of the oil tanker. A local failure such as those mentioned in the previous point will not extend into a global collapse. The progressive reduction of the steel section and the connected concrete compression in the stay would result in increased local displacement and significant deck level irregularities long before a near collapse. So it says that if the progressive reduction of the steel section would have given a lot of warning before the collapse, this one happened without a warning. The structural overstrength is so relevant that the bridge is generally compliant with seismic verification applying the actions considered today. So finally, you go to the last two, that is the 7 and 8. The loss of stay seems to be the final cause of collapse, regardless of the initiation of the collapse sequence. The possible initial cause of the collapse may thus be related to fatigue problems in the tendons near the tip of the antenna, or by the deterioration of the connection between stay and the transverse link. These local phenomena have not been explored because of lack of detailed data. Now, let me come to the demolition of the partly collapsed bridge. The bridge, of course, had to be demolished because the precarious situation in which the partly collapsed bridge was there, and all the buildings which are just underneath, they were under threat. So therefore, the bridge had to be demolished. There was no element of doubt on that. And moreover, the bridge was in distress in any case. Even the other components were in distress. So a very elaborate method was adopted for demolition or deconstruction, as you call it. The dismantling was one of the renowned party or renowned organization, which is in Italy or even all around the world. It is called Fagioli or Fagioli. I don't know how it is spelled, but this is one of the renowned company involved, specialized in heavy transportation and lifting. So the normal method of deconstruction is always to reverse the method of construction generally. That means whatever is the sequence of construction followed for deconstruction or demolition, you can just reverse that process. And that was easily adopted for the approaches, leaving aside this two tower cable stayed portion. That means because the last item was construction or erection of the Gerber beam, and so it was first brought down by strand jacks, and then the balance portion of the U frame, the V frame, and the cast in situ deck was dismantled, cut into sections, and brought down, and then transported outside. As far as the cable stayed portion is concerned, that could not be done for the simple reason that the original construction required auxiliary stay cables, and there was no way to put that kind of a system, and moreover it would have been time consuming. The time was a essence. So they resorted to blasting, explosion, and by demolition by explosion. But what is worth seeing is how they did that, keeping the safety environment in mind. That is something worth seeing. So you can see this shows how this Gerber beam is brought down first and then removed by using strand jacks. And the weight of each suspended span, including deck slab, is about 1,000 tons. This is you can see another picture of demolition or deconstruction. Coming to the main demolition of the main two towers and the overhanging portion, this was done by explosion. What you see, white lines are not really blasting; they are the water jets, which is also exploded to ensure that the dust is not spread. So the kind of precautions taken for demolition is something worth seeing. What I will show you is a small video on this. Give you a fairly good idea.
Morandi Bridge collapse killed 43 people.
I'm sorry for this. I think internet instability problem. I think there is some internet issue. I think we can move forward. Hello. Okay. So we just 2 minutes brief on that. This new bridge is now being designed or is being designed by one famous architect who is called Renzo Piano. He's a world renowned architect and he volunteered to help build this collapsed Morandi Bridge. He is basically a native of Genoa and he serves as a senator for life in the parliament of Italian parliament. And he actually stays with us, is a architect. So he took the responsibility for the design and the winning design is entirely stainless. The bridge features a continuous 1.1 kilometer steel deck instead of concrete. Now it is a steel deck, and with 19 spans. So this is the team. Uh, the uh, the architect, director, and the supervisor is Renzo Piano, a very famous world-renowned architect. The designer is Ital Fair, and the contractor and the quality control is by this agency, and Parjanova is the contractor. And this is a very high-tech job done with 7D beam technique. I think, I mean, I would not like to spend much time on this, but this is a smart and sustainable bridge with a lot of new features, robotic and sensor automation system for infrastructure monitoring. There are special dehumidification system inside the box for preventing the corrosion, low environmental impact. There are, solar cells available. The lighting for this entire bridge is basically from solar panels. There are structural health monitoring system embedded in this, which helps in sort of getting data on a regular basis. So there is a there are the one of the feature is having lamps, special lamps. There are 43 numbers of lamps installed, which basically is symbolic of 43 victims of this particular collapse. Uh, and this whole design is on the, is a replica of ships, different components of the ship, because being a port city, it it represents the culture and ethos of the people of Genoa, and that is the theme on which this particular bridge has been designed. These are various pictures of the bridge. It's a steel, basically it's a steel deck with concrete deck slab on top, but it was done in a record time, and the method of construction, method of design, all are done. I mean, there is a lot of things to learn here. There is one more, but there seems to be a problem in running the video. Let us see. This is the last video. So with that, I end my presentation. I think I have given you a broad overview of what happened and what is presently done. Thank you very much.
Okay, so thank you very much, Alok, for this masterful presentation is all I can say. I mean, you have really brought out so many issues in, the last 1 hour. It's almost unbelievable. You have started from even compared the concept of Morandi with cable stayed bridges. You have talked about Morandi and not only of his bridges, but other structures as well as those fancy arch bridges with the inclined, columns which support the deck, which is something unbelievable. I mean, the amount of creativity that seems to drip out of every structure that he has designed. You have also brought out the history of maintenance, or I would say history of maintenance or lack of it. I think that we have to see this in a particular in a context, which I will just talk to you in a minute. But it's a very good thing that you talked about this Calvi's paper and the software that they used, which is called AEM, and which can actually tell you the collapse mechanism, and as it collapses, parts of it, how the rest of the bridge is affected, which you cannot do with the finite element method, of course. One thing is certain, that you have concluded from all the literature, that really it was the collapse of the tie which was responsible. The collapse of the tie may have been caused by some whatever reason, but it was the tie which collapsed. And obviously, when you look at that structure, if the tie collapses, there is going to be a problem. It was also very interesting to see the demolition of the bridge, which I think was remarkable. The techniques, I think the amount of engineering that is required in demolition, I wonder if it is in any way inferior or less complicated than the design of the original structure, because it is so important. I have seen collapse these. If you remember the Oklahoma building, collapse the way when they demolished that. I don't know how many hundreds of columns and all they had, but that building was surrounded by other buildings, and the only way it could be done is to just collapse vertically. It's as if the whole building which is standing up sits down at the same place. It's almost like yoga. I mean, without moving this way or that way. So it's I think that was very interesting to see the demolition, and of course, finally, how well they have constructed the new bridge in record time, and this being a sort of a traffic, a highway, which is so important for the tourism industry connecting Italy and France. I mean, it is not only the bridge, it is much more than that. I mean, it is the economy of the two countries which are involved here. And to get that up in record time, I think in less than what you said, 2019 it started.
Yes.
Sorry?
2 years.
Total 2 years. Between collapse to the new construction is 2 years.
Yes, collapse, but it requires to design also. It requires, in India, it would take 2 years to appoint the consultant, if at all, or maybe make the tender for the consultancy.
Yeah.
So it was really remarkable, and thank you so much, Alok, for giving us the an insight into this. Now, may I ask our two panelists to give their comments, starting with Dr. Marioni,
Okay, thank you. Thank you, Professor.
would you like to add a few things to whatever Alok has said?
Yes, I can. Hello to everybody, and thank you for inviting me. If I may show some slides, not too many, because I think Mr. Alok already showed very, very comprehensive, but I have prepared some slides about the repair.
Kindly share, sir.
You cannot see my screen?
No, not yet.
No, you have to
Mr.
share your
Vikas.
screen. You have to share your
विकास के
screen.
पास में नहीं है?
नहीं, विकास के पास तो नहीं. I think he only has to share.
अच्छा, okay.
Ah, yes, yes.
Now you can see? Okay.
Yes, yes, we can see.
Okay, so now I skip
Please go ahead.
many slides because Mr. Alok already spoke. I only wish to say one thing, because the computation of Morandi has been discussed, but I was participating to a group called Save the Morandi Bridge, but we fail our scope. And we revised all the computation made by Professor Morandi, and this was perfect. Even if at the time of that Morandi made the computation, very simple, very limited computation tool were available. The slide rule that you see in the left, and the electromechanical calculator, and only for more complicated, but not so complicated as we do now, computation, the university or the IBM computing center was available. In any way, the computation of Morandi was perfect, has been revised. Now, the company of which I was chairman, company Alga, repaired the bridge in 1993. Why the bridge had to be repaired? For a construction mistake. If you remember how the construction was done, the stay cable were formed of steel strands embedded in the concrete. But during the construction phase, the steel strands were naked, and they were put in tension basically by the weight of the structure. So during the concreting of the pier, the steel strands had to be kept spaced by a steel truss on top of the pier. But this was for the pier 11 that we repaired. The steel truss on top of the pier was weak and collapsed during the concreting, so that all the strands were packed together and were not protected from the corrosion. So the corrosion in pier 11 in the stay cable grew very fast, also due to the marine environment. The repair works was designed in collaboration with some former collaborator of Morandi. Morandi already was passed away in '93, and executed by Alga Company, of which I was chairman. Why this problem happened? I am sorry, but I have to emphasize these problems. The contractor that was Impresa Condotte, that was belonging to the Italian state, made a very bad job, making mistakes, and what is even worse, hiddening these mistakes. And the engineer who was appointed to control the job did not properly check. I don't comment, but the possibility are only two: ignorance or corruption. And probably other mistakes were deliberately hidden in the structure. And this can maybe explain the collapse that happened in 2018. So the repair of Pier 11 was made by adding some special designed steel carpentry on top of the pier, and in this element were suitable to house and anchorages of supplementary stay cables. And so you see here the steel carpentry on top of the pier, and this was the element on the bottom of the stay cables. The supplementary stay cable were added around the concrete stay. The concrete stay was not demolished because this would have altered the stiffness of the bridge, but could not be simply cut because the concrete was not compressed, but inside the strand had a very high tension. So cutting the concrete would have a big compression, would make a big compression in the concrete, and the concrete would fail. So this was like a surgery operation. The installation of the new stay cable and the tensioning of the new cable was a surgery operation, because tensioning the stay cable, we had in the same time to deactivate the tension in the inside the existing stay. So this was the repair. This was the repair completed, and this you see the bridge before the collapse with the evident repair on the Pier 11. Maybe probably similar defects was inside the other piers, but what was the difference? In Pier 11, the defect was very, very evident because the corroded strands was near the surface. So you could touch the corroded strand with your hand. Probably in the other piers, similar defect happened, but was not possible to detect them by the existing investigation and tools. So here is the bridge after collapse, but Mr. Alok already explained everything very, very good and better than I could make. And now we can only make some conjecture, since the judiciary investigation are still pending and some documents are still under investigation secret. But the most credited hypothesis is that the collapse started with a failure of one stay cable of Pier 9. What is also important to say that recently the concessionaire of the bridge, that is ASPI, Motorway for Italy, Autostrade per l'Italia, officially claimed against the Italian Ministry of Public Works, because when they took over the concession of the motorway, they say the bridge was affected by hidden defect. And this was something that could not foreseen by them. And so they are claiming that the collapse is not their responsibility. But of course, the judgment is still pending, and we will, I don't know how long will still last. Now, what is interesting also is that the last vehicle that transited on the bridge before the collapse was a truck loading a steel coil of 35 tons. The truck was on the simply supported beam adjacent to the collapsed stay cable. The simply supported span failed down with the truck and with its load and the driver. And the driver, for a real miraculous, survived and provided valuable information. Of course, the 35 tons is a big load, but is much, much less than the design load, and could not be the reason for the collapse. But maybe is the last drop that broke the camel's back, how he say. So the primary reason for the collapse most probably is the bad execution, aggravated by lack of controls or impossibility of controls during and after the construction. A bridge of such importance should have a safety factor of more than 2 on the design load and more than 100 on the load of a single track, and should have a service life over 100 years without major maintenance. That was not the case. So, as was already mentioned by Mr. Alok, the dynamic of the collapse has been investigated by Professor Michele Calvi, utilizing a mathematical model and considering the initial failure of different elements. So, first, making the tie collapse after the beam, but what is interesting, that one other professor, that Professor Domaneschi of the University of Turin, put in parallel the dynamical analysis of Professor Calvi with the available, okay, these are the main aspect of the dynamic analysis of Professor Calvi, and he put in parallel the sequence of these figures, the dynamic behavior, with the available videos. And it's very interesting that the hypothesis of collapse of one stay cable is matching approximately, quite good, but quite good with the available videos. So you see, after 1 and 2 seconds, and after becomes the parallel less evident, but still works after 3 and 5 seconds, and after 6 and 7 seconds, and after 9 and 11 seconds. Okay, I don't speak about the new bridge because Mr. Alok already spoke very well about it, and so thank you for your attention. And
okay, thank you, Dr. Marioni, for giving us an insight into whatever repairs were done prior to the collapse on not what collapsed, but the neighboring pier. May I now request our very own Dr. Harshavardhan Subbarao to give his comments.
Thank you, Professor Tandon. Alok, I want to congratulate you on a truly marvelous lecture. I think it's an outstanding lecture you've given us today. You touched upon so many issues, as our moderator said, each worthy of a debate for later time. So you've set an agenda for us all to take up, and further issues that will be arising across what we've learned from your presentation today. But on the point of issues, there are many things that I would like to say. First of all, I'd like to tell you about forensic engineering. The paper which Alok speaks about was actually from a forensic engineering group where they came to us for review. I'm the chairman of this outstanding paper award committee, if I would say, vice chair now. I was chairman then. And we were completely stunned by the quality of the paper and investigation. But you can note in his own, it was one of the forensic engineering's probable. It is not, it is this. It is from whole to part, working out what are the various possibilities, ruling them out, and homing in on a certain set of possible causes or combined causes of failure. And that is how any forensic investigation is done anywhere in the world. Now, the issues there being, things are secretive, as Marioni said. Secretive in the sense what? It is a judicial inquiry. And when there is death in India, for example, we have a judicial inquiry, and we have a criminal negligence inquiry, a civil procedure court, and a criminal procedure court when there's death and negligence. So that different countries have different ways in dealing with the investigations itself, legal and commercial and civilian issues. So these are some issues I want to tell you. I want to tell you a little bit about the history of forensic engineering. In 1847 on the River Dee in the UK, very close to Chester, a bridge collapsed, which was done by the famous Robert Stevenson. And it was in cast iron, a new material of that time, thought to be a wonder material. And many bridges were cast iron, including the iron bridge, which we know about today. So what happened, the causes of failure, etc., are well investigated, but this set the theme for forensic engineering. The incident initiated a review process, which is generally followed by forensic engineers to this day. One, an investigation was performed by a lead engineer, appoint a lead engineer who examined the site of failure, collect materials. Three, perform testing and analyses for reviewed witness statements like the lorry driver. Recreated events, that is, the failure event has to be recreated as you saw in the AEM model, progressive collapse model work. You recreate the event, and from that you can back postulate the reasons why it might have failed. Then we formulate a report attributing causation of the structural failure. And like all modern investigations today, the failure analysis is never conclusive, as is evident even in today's presentation. It is not exactly this. It is a probable set of parameters which might have caused the failure. It is not identified truly as being one, a unique one, and to determine the most probable cause. Okay, so this is what I want to say. What happened in 1947 when that bridge collapsed with the train going over it, the days of the steam engine, industrial revolution and all. This was before steel came into being. It was cast iron, wrought iron. It was understood that fatigue was the phenomena which led to the failure. And because of that, the whole science of fatigue came into being in bridge and structural engineering. And because of that, we developed modern steels. So lessons are learned from every failure. Another point I want to make, every failure leads to changes in codes. Every failure leads to our increased understanding and sometimes progress in material. That's how steel came into being in the use for steel bridges at the turn of the Industrial Revolution. So these are all factors that I just want to share with you. A 1947 event which created this concept of forensic engineering. In India, we don't have anybody called a forensic engineer. There is no kind of forensic specialist engineers, whereas in many other countries, you have registered specialist forensic engineers in their domain knowledge of expertise, in bridges, in cooling towers, or buildings. So domain knowledge is also different. And this is what I want to share with you about this. Expert witness testimony is commonplace to determine civil and criminal liabilities. As I told you, this is the process we followed in India. In the US, it is sue him, get your money. Everything is about money in the US. In the Europe, it is different. The procedures are different. They're not so go to court type minded, though court procedures will be there. The professional practice of forensic engineering, I want to read to you from a 2017 edition of the ABSE, special edition of the ABSE journal. The ABSE journal reads in the introduction, the professional practice of civil engineer of forensic structural engineering includes discussions of what structural failure is, the origins and the causes of the failure, types of cases of failures, importance of codes and standards, the standards of care or duty of care of the design professionals, and duty to perform for the contractors. Brief outline of the processes of forensic investigation are always enshrined with references to detailed publications, etc. to back up, as Alok has demonstrated today, an excellent research that he has done from the net, from Professor Calvi's paper, which won an award, as I told you. And the story has been put together to you of an outstanding bridge and the lessons that we have learned today. But notwithstanding that, the Maracaibo Bridge is still in existence. Many of Morandi's bridges are still in service of the same structural type. Although we may say that they lack redundancy, therefore they lack robustness, because there are only one set of ties, and failure of any one tie will lead to the collapse of the whole bridge. And there may be postulates of an explosive load, an impact load, any form of an impact load, or the Gerber span failing due to shear failures on the halving joint. These are all postulates until we get to see the wires and understand the fretting fatigue that might have happened. understand the way the wires and strands have failed, if at all, their loss of diameter and therefore the loss of carrying capacity, we will not be able to exactly conclude even the most probable cause. We have only now down to a set of probable causes, not the most unique cause. And that is what I want you to understand. And invariably, forensic engineering investigations are multidisciplinary. You might need a metallurgist. You might need a geotechnical specialist. You might need a construction person. You might need a highly advanced AEM type person, which is not the common domain knowledge even of a structural engineer, advanced progressive collapse work. So you may have even legal people involved if it's a legally oriented thing. So this is what I want to tell you, that we need to develop the science of forensic investigation in India. We lack it. Our process is just appoint willy-nilly 3 experts, and overnight they should produce a report within 3 days, and Willy Bob your uncle, all sort, blame is given, and the man's in jail. Pick up the structural engineer, put him in jail, pick up the contractor, put him in jail, and then we will have them weakened, enervated, on their knees, and then we shall dictate what they should do or what they shouldn't do, and where we will put the blame. This blame game theory has to be removed. And for this, I suggest we adopt what we call the cross model. Mr. Alistair Sohn, he has developed for the UK a wonderful confidential reporting system called CROSS. And you can go to safetyorganization.com on the net, and you can find for yourself the wonderful work that CROSS is doing. And recently, just about 2 months ago, after the Grenfell event and the investigation of the Grenfell fire disaster in London, they have now been given regulatory authority. The body that he formed has now become a Parliament Act and has become like a regulatory body for these issues. There are more than 1,000 reports which are free to you and me to read, and they give alerts. And the way they go about it is not to fix blame. The idea is not to fix blame. The reporting is confidential. The reporting is to be shared, and no blame philosophy. We speak about in those reports the engineering, the principles, and the ethics. We are not here to say the contractor is wrong or the consultant is wrong. Please read one CROSS report. It is so wonderful to read and learn, and read one of their alerts on which they issue alerts on things wrong with buildings or fire damage, fire protection. They put an alert on their website. Don't do this. These are lessons learned, And of course, they then influence policy, and they influence change in codes and in acts of parliament and the like. So they have been able to mobilize as a voluntary body and become almost a regulatory framework. And this is what I'm asking IAStructE and all others to join together and form such a movement, which should be independent, transparent, confidential, with the idea to improve the profession as a whole, and to learn from our lessons and learn lessons from failures and improve as a whole the overall profession. That's my plea. Alok, again, I thank you for this wonderful discussion and presentation. It has raised many thoughts, many issues, many ideas, and I'm sure it will raise a sense of inquiry and debate for some time to come amongst all our engineers. Professor Tandon, I thank you, and Agostino Marioni, I thank you too. It's wonderful to see you. As I said before, you're a friend.
Thank you.
Okay, thank
Just
you.
like so many others.
Thank you very much.
Thank you, Harsha. Thank
Thank
you
you.
very much. I think the people who have spent so much time on this, participating in this webinar, number of you can call them questions in a way, but because they were in that box, I have gone through them. 75% of them are in praise of the IAStructE, Mr. Alok Bhowmick, and the wonderful presentation that he has made, and how much they have learned from this webinar. So 75% are those. About 20% of them are that people want a copy of the presentation, etc. I'm sure this will be put on the YouTube or something like that. Anyway, you will be hearing about that in due course. I have selected a few only because it's already time to finish the thing. So I have just taken out a few questions with the apologies to everybody else, which I thought would be interesting for the panelists to react to. Mr. Vinay Gupta asks for cables, there will be larger elongation of the concrete encasement during variable forces. Will it not crack the concrete and become a durability issue for the cables? Who would like to answer this?
I can answer.
Yes,
I can answer.
Dr. Marioni.
First of all, as Mr. Alok very well explained it, in the concrete stay cables, there were two groups of strands. One was tensioned by the self-weight of the bridge, and the second group was stressed after that. So the concrete had a little compression. So this to prevent the tension in the concrete and the cracking of the concrete. And to the second question, to have only one stay, of course, is not a very good solution, and now nobody more would design a cable stay bridge like this.
Okay, thank you.
Okay.
Professor Prem, sorry, were you saying something,
Okay.
Dr. Mariani? Okay. Professor Prem Krishna has a comment. In 1960, not only were the cable-stayed bridges in a nascent stage, there were no big computers available, which inhibited designers from making their bridges highly indeterminate. That may also explain a single tie. Would anybody want to venture out, or you want me to reply?
Yeah, Mahesh, go ahead. Go ahead.
Okay. I can tell you that when we are talking about the time that this bridge was designed, there was really, truthfully speaking, no concept of durability. We thought that when you make something in concrete, it lasts forever. As a matter of fact, concrete was synonymous with something which is durable and strong. And we never thought beyond that. As a matter of fact, when we did the Indian Airlines hangar, which has also got a single tie, as you may have seen in the slide that Alok showed, we had the same idea. The first idea was to put more ties, but we said, no, it's not necessary. But there is one or two differences that we did make. Although the durability aspect was not known at that stage to that extent, I had a feeling that you must have a very high strength concrete, which is very important. At that stage, to make M50 concrete, you cannot imagine. This was in the 1970. To make M50 concrete, the contractor wanted almost double the cost of the hangar roof, because he says that he has not provided for it. And those were the days when people were still doing volume batching, which was always an option. So that is one precaution we took at that stage. The second thing that we did not stress the cables first and then put the concrete around it. We didn't want to risk that at all. There was no reinforcement in the tie. It was only concrete surrounding the cables. But we first constructed the concrete tie. The pre-stressing cables were already there, and then we stressed it in the hope that this whole tie would come into compression, not half and half as was done in the case of the Genoa Bridge. So these are two differences which I would like to point out that we did even at that stage. Not that there were any sort of written documents about it, but it was just a feeling that that's what the direction in which we have to go. And incidentally, that Indian Airlines hangar was also designed on a slide rule. The first mechanical calculator that came to our office was around the time that the construction of the bridge of the roof was going on, and when at that time it was a world record roof cantilever. It had a total thickness of about collapse thickness of about 6 inches, I think. So 6 inches, that means 150 millimeter is the total thickness of concrete. average, going over some 60 odd meters cantilever, which I think was quite remarkable at that stage. So far, God forbid nothing happens to it. Let's not talk too early, because that was only constructed in the 70s. So it's not as old as the Genoa Bridge perhaps, but more or less at the same time.
But Professor Tandon, any feedback? Any feedback on performance now? I mean, what is the?
Well, I only want to say that first I want to thank Stoop Consultants, because at that stage when I was designing this, I had 3 years of experience, and for them to put the trust of designing such a complicated structure in me at that stage, I think I'll be forever grateful to Stoop, because that is where I started my career, and that is where I got inspired, and in structural engineering I remained there. And as far as I know, there is no feedback. Otherwise, I'm sure that I still have friends in Stoop, and they would at least tell me if there is anything that is going wrong or something like that.
No,
Sometimes no news may be a good news.
No, Alok, that's not.
Yes.
There was an extensive investigation done, detailed NDT and all, because it's a folded plate. There was an extensive NDT investigation done more than 20 odd years ago, and it was in the first FIB days that we started in India, the first FIB days. There's a paper there by Joglekar about that. So there was a detailed investigation and corrosion and all that was done and documented at around that time. I don't know about current day what the situation is.
No, you see, when the project finished, we advised Indian Airlines. That means Stoop advised Indian Airlines that we should continue. A part of they gave us a separate letter of, extending the contract, that you have to monitor whatever is going on. They agreed with it. And we did that for a few years. And then Indian Airlines, the moment the, people changed, they said, why are we spending all this money and giving it to
Right.
Stoop for looking at the thing? Everything is fine. It's made of concrete. Nothing happens to concrete. So the contract was finished, and there was no more connection of going to the site, visiting those bridges. I still remember climbing that the stay cable like a monkey right up when the bridge was under construction, and everybody else who was on the roof at that stage was praying that I would come down safe. But I was more intent on reaching the top, because it was really like going on a Mount Everest. Okay, so that's enough about the Indian Airlines hangar. Let me talk about Mr. Sanjay Chaudhary. Is the new bridge on the same alignment? Then how the new foundations were done, keeping in mind the congested area, or the new bridge was done on old foundations? In that case, how it was ensured that the old foundations were not distressed due to something,
Right. No,
due to the loads, basically.
Mr. Marioni can reply.
Blasting, due to blasting of A-frame. How are we sure? Is it on the same alignment, firstly?
No. First of all, it's not exactly on the same alignment. And second, frankly, I don't know how they solved the problem of the foundation in that congested area. I don't know. Frankly, I don't know.
A question by Mr. Sukalayam Sarkar. What were the instruments installed for structural health monitoring of the new Genoa Bridge? He's not talking about the old one, talking about the new one. Does anybody know?
Also, I am not able to answer. No.
I can tell you, all these informations are available. Just you have to scan through the internet. It is available. I mean, this is a classic example of a highest order of project management which was engaged. This is a 7D. Normally we talk about 3D beam modeling. This is a 7D where structural health monitoring is a very much embedded part of the scheme of things. And I'm sure the question can be answered.
So the answer is at the internet, basically, if you want to get
Internet,
into details of this.
Yes, yes.
The next question from Mr. Vinay Gupta. Single tie stay cable bridges should not be permitted in future due lack of redundancy.
Nobody would.
I think
do
this
it.
we have already discussed and answered.
Nobody would do it.
But Mr. Vinay Gupta, please pray for the Indian Airlines hangar. It has got only a single tie, just as the Maracaibo Bridge, thanks to the inspiration given by it.
But now,
the-
Mahesh, you don't have any liability for it. It's a different company now, right?
Well, you can't say you are not responsible for your own child.
Of course. That's the point.
Yeah.
Mr. Shiv Kumar Kandasamy asks, was the demolished concrete recycled and used as aggregate in construction of the new bridge? Please let me know. Thanks.
Certainly not in the new bridge, because the new bridge is a steel bridge. And I don't know, probably Mr. Marioni can throw some light on that.
No, I think this concrete has been used to make some artificial platform in the sea, to fill the sea and but I'm not sure about it.
Right.
But the total debris was about 50,000 tons.
I think more than that. I think
More than that.
100,000.
Okay, but
Okay.
they still have a hell of a lot. 50,000 or 100,000.
But
I don't know what did they do to it would be interesting, because that is also a
Another area.
environmental hazard as to how to dispose of this. It's not only a question of recycling and reusing, that is of course the higher end of it, but also way to dispose it of what you can't recycle and reuse. Next question. I'm leaving out the questions, like I said, which are all in praise of Alok, Bhowmick, IAStructE, and the presentation. I'm not doing that. I'm once again thanking everybody for that, and thank you for the encouragement, and we will have more such webinars, hopefully.
Yeah, this
They
is
will
very
be as
motivating.
good as the one that you have attended now. What are the controlling mechanisms? This is Krishna Dikshit. Krishna can be Ms. or it can be Mr. I don't know which. What are the controlling mechanism of monitoring the elongations and stress due to temperature variations in the strands cables? Anybody like to volunteer?
What's the question again?
What are the controlling mechanism of monitoring the elongation and stress due to temperature variations in the strands on cables? What he's meaning, I think, is that once you have put the bridge in service and there are temperature variations, is there a controlling, how do you monitor what the temperatures are and what effects it has on the structure?
Cable tension?
You monitor strains on the surface, and from you can find out what is the temperature gradient. If there is any other method, I think maybe you can enlighten us.
In fact, once you enshroud something in concrete, it's very difficult to get tensions in the cable directly. So only indirect means can be adopted. You can, whatever surface strains you can get, but for that, you should have known the set of strains across time. Those strains which are changing with time-dependent phenomena and non-time dependent phenomena initial. So it's quite, you're shooting in the dark quite a bit, I would say, to assess that with a direct sort of measurement. It's not possible.
Okay, I think we'll take the last question because we really overshot the time. Mr. Amitabh Ghoshal, apart from, of course, very educative event, shows that concepts keep on changing and structures tend to be vulnerable. It suggests the importance of review of design of important structures at certain interval. I think what he means to say is that after the bridge is constructed, there should still be a review. Of course, the design has to be reviewed at the either before or during construction or whatever. But I think he's talking about a review even thereafter, because the concepts keep changing. For example, if this was a a single tie that we are talking about, whereas now it's nobody's using it, there should have been a review of this design itself, whether there are any frailties which may result in a collapse like the one that happened. Of course, it happened, I think, due to neglect and lack of maintenance, but that is my view. But this is what Mr. Amitabh Ghoshal is saying. Any views on the subject?
Can I say something?
Yes, please.
The cross that we are talking about, we are very much involved with them in both the journal, as well as he's a member of the journal, Alistair Shawn, and some of his colleagues, the Institute of Engineers UK Journal on Forensic Engineering. He's involved with that. And he's also involved with our working group in the ABSE, the task group TG 5.1 and the failure database 1.5, TG 1.5 of ABSE. So I meet him and I talk to him online very often. I'm very much hopeful, Mahesh, that we can somehow get across, and now CROSS has gone international. So if we choose to, we can support them and adopt their system of confidential reporting. They will help us set up and everything. And we can start CROSS India. I mean, just CROSS UK was launched a year ago. So CROSS is now available in their system in about 7 or 8 countries, including Australia. It's not UK alone. So Germany. So there is no reason why we can't adopt a confidential reporting system and format, which would be non-blame oriented. So that is a crying need. The other point I want to make about, which Ghoshal Sahib has also addressed, is this new idea that we have, or this newfangled thing that is happening in forensic engineering. It's called legacy reports. So a structure which is old and some things were done then, and time has gone by, lessons learned them have been forgotten. And suddenly now we come across a collapse and we realize, oh, that structure at that time, a legacy issue. So something that happened years ago and how it might resonate with current sort of issues are lessons to be learned. They're called legacy reports, and CROSS has a number of them, which I would again entail you to read. So CROSS has more than 1,000 reports online. So this is something worth reading and simple to read, not so heavy or anything.
Harsha, if I may suggest, can you at least share with all the participants the link?
Yeah, structural-safety.org, structural-safety.org. Structural-safety.org is the link.
I think just send it to,
we'll send it to all
Mr. Vikas, who can perhaps share it with the participants.
All the participants.
Oh, there is another comment from Mr. Satish Dhupelia. Dr. Tandon, I am not doctor, I am professor. Slide rules were the best means of calculations. They cannot go wrong. Unlike advanced softwares now, prone to a like junk in and junk out. Okay. Any disagreement with that?
I fully agree, because I also started with that.
Can I also make
I would just repeat what Professor Holger Svensson mentioned in one of his lecture. He says, if you do a calculation, then you can go 20% wrong. If you do a computer calculation, you can go 200% wrong also.
Yes, that's true.
That is the importance of preliminary design in the cable state lectures that he gave us. Very important to know preliminary design and conceptual design.
And if I may add,
which is not taught in our course.
Sorry. Harsha, you please complete what you were saying.
I just want to say there is also a task group on 1.5, which has more than 3,000 bridge failure cases, which I think will now produce a report, which then I think, Alok, then we should have a session to discuss bridge failures, lessons learned, and all that, the statistical implication of that, when that comes out. Okay, so that's a promise we can keep to our audience. One thing. The other thing I want to also say is, this idea of putting someone in jail and this liability and criminal liabilities and all that are apportioned unfairly onto structural engineers and contractors when there's a collapse at site, as recently happened in Sona. I mean, we have to finally thrash this out. We need to be heard. We need to get our voice raised. and we need to take action. The time has come where I have seen often that the structural engineers simply apprehended or put into a state of fear, and no organization is there strong enough to support them or stand by them or appoint a lawyer or bail them out or whatever it is. There is no supportive action through any institution, and they are left on their own and in fear. No innovation can happen if the sense of fear is kept in the minds of those who want to innovate. They have to be free to experiment. Failures will happen. We will learn from those failures and change things. It is not that you can innovate without having this idea that things will not fail. You hope that it won't happen, but you should not be scared to innovate if you're filled only with fear. So my suggestion is that innovation should be allowed and not stifled because of this fear that is set into the minds of structural engineers and others, that if I do something risky, if I go to the limit, or if I push the material a little more than what the code says, and I can prove that it is all right by experiment or by my own analysis, and I can stand by what I say, and I'm prepared to stand by what I say. If tomorrow there is a failure, I mean, where is the liability? These issues of liability, the apportioning of risk is directly on the structural engineer, and there's nothing that can be done. More or less, hardly anything is, the reputation is instantly destroyed. So I want to raise the badge that these are the discussions that we need to flag and have, and our institutions, IAStructE and IAB and Institutes of Civils and ECI or what have you, all have to come together with this issue of liability towards the engineer and what steps can be taken to mitigate that and how we can be heard. These are issues which are before us in India, and we have to take them up.
Okay, thank you, Harsha. And I think that you have given more food for thought to Alok. He's always wrestling with what is coming next and what is the next seminar or webinar that we are going to take up. So you've given him enough ideas. I just have one last comment to make. And that is that, we have been talking about this computers and the slide rule. I can only say one thing, that the computers, apart from doing a lot of other damage, that means that they have damaged your brain cells. They have also squeezed out the romance which existed in structural engineering. Because if you can press a button and, get the result, where is it? Where is the romance in all this? There is no romance. You just press a button. If you press the wrong button or enter the wrong figure in the input data, you get something else, finished. So it's really a tragedy. But anyway, we have to move with times. We cannot be in the slide rule age anymore. So with that, I think if anybody wants to make any further comments before I close the session?
No, we thank you very much, and was a very wonderful, wonderful webinar. Thank you.
Thank you.
Excellent.
I must thank Professor Tandon and both Professor Marioni and Dr. Subbarao and all the participants for accepting and for praising this particular webinar, and this gives me a lot of encouragement, and I'm sure I will expect many participants who has some story like this about the failure to come forward, and we will provide the platform for this similar kind of webinar where we can learn lessons from the failure. Thank you.
Okay, so thank you very much to Mr. Alok Bhowmick, Dr. Harsha, Dr. Marioni, and of course, most of all, to all the participants and the people who have taken the trouble to post all their views and questions on the chat box. Very grateful to them, because really a webinar has got no use unless there are participants. And I think that, and there is a participation of the participants. And I think that it has been able to achieve. So I'm very happy with it. I think with that, we can close the session and have a good night.
Thank you.
Thank you.